Howdy everyone, and welcome back. And today we're going to do another review. We're going to look at some of the last week's topics that we've been talking about, sort of putting together, do a number of problems, going over them, hopefully get ready for any tests or exams you have going up. Okay, let's do it. Again, it's going to be something where I haven't really looked too much at the practice tests, so we'll see what happens. Maybe it goes awful, we don't know, so we'll figure it out. So let's start and talk about just some of the equations we're going to use and what did we actually talk about the last few weeks. So assuming some type of second exam. But chapter 17, we talked about current, we talked about basics of direct current circuits, we talked about Ohm's law, we talked about how you could calculate the resistance using the resistivity for a resistor. We talked about how resistors are temperature dependent. We talked about how resistors, output some amount of power in terms of heat when you put electricity over them. We talked about current. Chapter 18, we kept going with this idea with direct current circuits. We learned how to combine resistors together, and if they're in series or if they're in parallel. We learned about Kirchhoff's laws, which are some of the most fundamental things about direct current circuits. We'll learn that if we go in a loop in a circuit, that if we'll add all the voltages together, they have to be equal to zero. So I didn't create or destroy any energy. It's the same amount of energy when I get back to the beginning. And then we learned the junction rule. So when I get to a junction, the current splits, and then they all have to add to each other's. And now charge is conserved. Current didn't go anywhere. It didn't get created from anywhere. It just it was coming from here and went that direction instead. So it's always conserved. Chapter 19, we started talking about magnetic fields. We learned how to calculate the magnetic force on a charge and on a wire. So here I have a charge and on a wire, and it's dependent on there both being a magnetic field. There has to be a charge present, and that charge has to be moving. So the same thing down here, the charge and that it's moving, it has some length of wire, and there has to be a magnetic field, and there has to be some type, the angle between the magnetic field and how it's moving. If they're pointing the same way, sine of 0 equals 0. So we also learned a couple ways to calculate the magnetic field from a few basic shapes, and one is just a normal parallel wire. One of them is a solenoid, and we also learned how to calculate the torque on a loop of wire using a number of terms. So we kept going with that of chapter 20, talking about these loops of wires and what happens to them, and we talked about Faraday's law. So this is when you have a changing magnetic flux. If it changes over time, it will actually produce an EMF or a voltage in that loop. It'll create a current. That is the heart of Faraday's law. You need some type of change, and magnetic flux, we define that. In chapter 21, we talked about alternating current circuits. It's pretty much, a lot of these things are pretty similar to DC circuits, except we have to change some of the definitions. We have to change from normal voltage to some type of average-ish voltage. We call this root mean squared. Maybe you can use the full amplitude, or we could still use a similar equation. But a lot of the equations like Ohm's law that we learned before, like again, here's Ohm's law up here, are still valid, but we just have to change the definition. And there's another type of thing, impedance, which is like resistance. Again, it enters in Ohm's law the same sort of way, but now it's dependent on frequency. It's dependent on if there's any inductors or capacitors involved. Okay, so it's kind of a jumble of a ton of stuff. Big emphasis on circuits. That's the vast majority of what we've been talking about, although we had a subtopic talking about magnetic fields and a bit how magnetic fields enter in circuits with inductors. So basically, circuits and magnetic fields are the main topics. So we're going to do a number of problems regarding both of these things. A lot of these things can be kind of mathematically difficult, but definitely conceptually difficult. Magnetic fields are very conceptually difficult because they don't really act how we expect. I mean, maybe we can sort of buy into how when we learned about electric fields, how they act, they just push and pull on each other because they exist. But magnetic fields things moving, and then they can changing magnetic fluxes can create voltages. It's a lot of weird stuff. So a lot of things to keep in our mind. So let's start doing problems. So I have some practice midterm. We'll go over it. So we have a circuit. We have some type of battery and a bunch of resistors. The current in amps flowing through the 10 ohm resistor in the circuit above is, well, we don't know. So we need to figure out generally the current flowing through the circuit. So there's going to be a bunch of different currents. These are going to be the same. But first figure out this overall current, we're going to have to reduce this down to an equivalent resistor. So we have to use all of our rules with parallel and series. So what should we do first? Well, we see that these three things are in parallel, so we should use the parallel rule. Then we get rid of them, and we'll have just one parallel resistor with that whatever that equivalent resistance is. So let's go do that. So how do we calculate it? Well, we do that 1 over R rule. R equivalent equals 1 over 5 plus 1 over 10 plus 1 over 5. Now let me see if I can do most of this without a calculator. This is 2 over 10, 1 over 10, 2 over 10. So overall, that's 5 over 10, and then we invert that. So it's going to be 10 over 5, so that's just going to be 2 ohms. So I replace these, these two things right here. This one equivalent resistor is going to be 2 ohms. So I have a 2 ohm, and then I have another 2 ohm. So the total equivalent resistance, let me do this. Total equivalent resistance is going to be 2 ohms plus 2 ohms. It's going to be 4 ohms. So that means we can go back and calculate a lot of this stuff. So we can go back and get the overall current using V equals IR. We solve for the current. It's V over R. So it's going to be 20 volts over 4 ohms. So there's an overall 5 amps moving through this outer part of this circuit. So this is 5 amps. This is 5 amps here. So we can sort of see what happens. So this 5 amps gets split between these 3 resistors. So what direction will it want to go? Well, most of it will want to go through these two. It doesn't really want to go through this one as much. So to calculate the, not going through that, we're going to have to use a few more rules. So we need to use, likely going to use the junction rule. So it doesn't really matter where the split is. The overall thing is this 5 amps is going to equal all these 3 added together. If we can sort of take these two and, we know it's going to be the same current for each, so maybe that'll come into play in a bit. So we know that this overall current, I equivalent, I'm going to say the I through the 5 ohm one, the I through the 10, and the I through the 5. So we know these are going to be the same. So I'm just going to group these together. 2 I5s plus an I10. We know this is the 5 ohms right here. So we essentially want to solve for this thing. So how do we break this degeneracy? How do we end up solving for this? Because we have 2 unknowns, we want one thing. Well, we're going to have to use the other Kirchhoff law, which is that the voltages over things in parallel have to be the same. So these two things, when I go in a loop, I have to have the voltages add to 0. I have a current going this way, a current going this way, so one of them ends up adding positively. That's this one. This one ends up adding negatively, but the point is that the voltages we'll find are going to equal between these two. So I'm going to say the voltage over 5 is going to equal the voltage over 10. So how do we write that a different way? Well, we can write that using Ohm's law, and we can go make a substitution. So we can always substitute these things between each other. So what do we want? Well, we want to figure out I10, so we don't want to replace that. So let's replace I5 and put it in there. So we can write I5 as I10, R10 over R5, and we know what the resistance of the 10 and 5 are. It's 10 and 5. So it's essentially saying that the current going through the 5th one is going to be just the 10th one except times 2. So let's go put that in. We get 2 times, and we're going to put this in, I10 times 2 plus I10. So we get 5 times I10. So this is 5 amps. I10 is going to equal 1. Is that an answer? It is an answer. So we're saying answer is that one. It's going to be 1 amp. Okay, let's keep going. So now we have another circuit. Consider the circuit shown in the figure. In this circuit, Ri is the internal resistance. So that's this one. R0 is an external resistance, and AB are battery terminals, and S is a switch. So find the power dissipated at R0 when the switch is closed. So if we wanted to calculate power, it's always going to be P equals IV. Okay, that's interesting. So we have essentially 2 resistors, And we can always combine them and do equivalent resistance and work back. So one thing we notice is that these are in series, so they're gonna have the same amperage going through and the same amount of current going through each of them. So that's gonna end up being useful. They don't necessarily have the same voltages over them, so we have to sort of figure that out. So overall voltage of E naught when we go through this loop. Okay, so we want to find the power going through R naught. So we're going to have to find the current going through R naught. We need to find the voltage going through R naught. So our goal is going to be to find this thing. So how do we figure out how much voltage? Well, we can do Kirchhoff's law. So we go in a loop, all the voltages have to add to 1. So when this one adds voltages, these two have to take it away. So we can write that as E naught equals VR naught plus VRI. Yeah, that's fine. Okay, and then we still haven't solved it because I don't know what this thing is right here. I don't quite know how to write that down. Well, again, we can go back and keep working on this equation. We can use V equals IR. We can always use Ohm's law. So I get IR naught times R naught plus IRI plus, I think they used a little r, and I think I'm going to confuse myself. So yeah. So the thing is, these are the same currents. So these are actually the same thing. So I'm just going to call them I. So we have I R naught plus RI. So that's what this E naught thing is. So why is this helpful yet? Well, we can write this in a slightly different version using V equals IR. So we can get, I want to replace it with the normal I R squared, I R naught. We essentially can solve for this I here. So we move this stuff over and we have this I. So essentially I equals, I've run out of space, but it's going to be equal E naught over that stuff. So it's going to be E naught R naught plus RI. That gets squared R naught. Okay, are there any of them that look like that? There are, so this one is exactly that. So I think that's going to be our answer here. I think that makes sense. Let's do the proportion of each of them. So does this answer make sense if we go and test some limits? So say that RI essentially disappears and resistance go to 0. Well, if we go get rid of this thing, essentially it just becomes V equals IR and this overall term, and essentially we just write this as the I squared R version where we replace I with V equals IR. So that makes sense. That matches. You can always go back and do a number of these checks when solving for these problems. Put in a limit. What happens when R naught's really big? What happens when R naught's really small? Well, when R naught's really small, you have something that goes as 1 over R naught squared times R naught. So this is going to, thing on the bottom is going to go way faster than the thing on the top. So essentially the power is going to go to 0 because most of the power is going to end up dissipating here instead of here. So I think a lot of these are implying that this answer makes sense. Okay, we should move on. Keep going. Which diagram correctly shows the magnetic field lines created by a circular current loop which flows in the direction shown. So again, we have to think back to the right-hand rule, and we've learned 2 of them, but one of them is from the magnetic field created from a wire. And if you have a wire, put your hand in the direction that the current's moving, or put your thumb in the direction that the current's moving, and you can wrap your hand around, and the magnetic field is doing this 3D effect where it's wrapping around this parallel wire going in this direction. It's going around. So a lot of these immediately don't make sense. You're not going to get anything that looks like this. We're going to get something that looks like these last two. But which direction? So I'm going to pick right here, I'm going to pick right here, and then we can sort of see what direction the magnetic field's going. So on the right side of this, you point our hand, point our thumb in this direction, wrap it around, and so we should see it should go around this way. If we're pointing into the camera right here, the magnetic field should go around this way. So it should do this, not this. So that's not our answer. Should be this one. Okay, not too bad. Especially a lot of these conceptual questions could go really quick if we're very confident and we know what we're doing. Okay, let's keep going. Okay, consider a square loop lying in the XY plane. So this is in some flat plane. a constant magnetic field is anti-parallel to the x-axis, is going the opposite direction of the x-axis. This figure, the z-axis points out of the page, so that means it's pointing towards us. You know, you can, if you know about cross products, if you can do the right hand rule with the x, y, point your hand in direction x, curl it in terms of y, z should be pointing with your thumb, so it is coming out like this. Okay, determine the direction the loop would rotate when in the position shown. So we need to figure out, with this current going around, how is this magnetic field going to affect it? So we can pick either of these sides. So I'm going to pick the one on the right. It turns out, you know, current going the same direction or opposite direction of magnetic fields doesn't do anything because have that sine theta rule. So if you look at the force of a magnetic field on a wire, if this angle here is 0 or 180 degrees, sine ends up being 0. So the point is that the only two things that matter are these two ends. So let's just pick one, and that'll sort of tell us where we're going. Okay. We're going to use the other right hand rule this time. We point our hand in the direction of the current, so that's pointing up. We curl it in the direction of the magnetic field, so that's going to be pointing to my left. It's going to be pointing this direction, and then the force is going to be pointing out of the page. It's going to be pointing in the positive z direction. So the force is going to be hard to draw. Yeah, this is, you know, coming out of the page here. So force magnetic field on the wire is pointing out like this. It turns out if you go over on the left side and do the same thing, I point my hand in the direction of the current, which is down. I curl it direction of the magnetic field, which is left. I find the force is now pointing in the negative z direction, so it's going like this. Or again, it's a right angle. Okay, what does that mean? So we have a few options. Would the loop not rotate? Well, we're looking at the axis of rotation here in this middle section. So it would rotate if we had the axis going horizontally, you know, then that's going to be funny. It's not going to rotate. So we're going to get some type of rotation, but is it clockwise or counterclockwise? So we're going to ask the question when viewed from above. So it's going to be pushed, we're looking at from above, it's going to be pushed this direction and we're going this direction, so that's going to look clockwise. It's going to look clockwise, so that's going to be our answer here. Okay, here we go. Still conceptual. That's good. That's good. So part of a long straight wire carrying current I1 is shown in the diagram. A rectangular loop of wire has dimensions A, cross B, and carrying a clockwise current I2. Is placed on the longer side is parallel to the long straight wires illustrated. The side parallel to and nearest to the long wire is perpendicular distance. Okay. You're given, okay, you know, and we know that magnetic fields created from a single wire, so they're being created from here. So point our thumb in the direction of the current, wrap it around, so the magnetic field's going to be looking like this. And we know that the strength goes as this equation, mu naught I over 2 pi r. So what's going to be correct? So firstly, again, we're not going to have to care about all aspects of this loop. Let me think about it. So the magnetic field is going to be going into the page everywhere. So sometimes we draw that as, you know, this, where we have these X's everywhere. So every single point is going to be going into the page. But we're going to notice an interesting effect. So the magnetic field, since it goes as 1 over 2 pi r, it's going to be a lot stronger over here on this side than it's going to be on this side. So there's not going to be quite an equal effect, and I think that's where this problem is going. So at the same time, current's wrapping around. Current's wrapping around. So we're going to have to use our hands and figure out what's going on in each segment of here. So, and I'm going to keep note with the force with green. So let's start on the bottom. We put our hand in the direction of the current, which is to the left. We curl it in the direction of the magnetic field, which is into the page. We'll find that the force exerted down here is down. We go, let's try the left side now. So the current is pointing up, curl it in the direction of B field. Okay, the force is pointing to the left. Okay, same thing on the top. Point our hand in the direction of the current to the right, curl it in the direction of B field. Force is pointing up again. So it turns out that the forces here on the top and the bottom will be exactly equal because essentially the identical lengths along here. And although it's a little stronger here, but it's also same strength here, but it's pointing in the opposite direction. So it just turns out this will completely cancel out. Okay, but let's do the last portion. So current's pointing down, curl it in the direction of the B field. Force is going to be pointing to the right. But notice, because it's farther away, this one's going to be weaker. So we actually could write this, draw this as this. This is going to be the strongest force on the left, and this one on the right will be actually pretty weak. So something might end up happening. So let's look at our options. The rectangular loop experiences a net force directed down and perpendicular to the plane of the diagram. So no. The rectangular loop does not experience a resultant force, but does experience a torque. So it doesn't look like it's going to be torquing here. None of the forces are going to be into or out of the page. They're all actually in the page. They're actually causing it to spread apart somewhat. So that's not going to be the right answer either. So let's mark these off. The rectangular loop experiences a net force directed up out of and perpendicular to the plane. That doesn't see. So it's going to be, it's going to be attracted to the long straight wire because this force on the left is going to be stronger than the one on the right. Again, it has to do with this 1 over 2 pi r. So if you computed the force, which looks like IL B sine theta, so we actually calculated this portion of this, it goes mu naught I over 2 pi r. This r term is going to be different from here and then from here. So it's going to be a lot larger of a number all the way on the right. It's going to be a smaller force. Okay, that's essentially what's going on in that problem. Okay, let's keep going. Okay, we're going to do some math. We're going to do some math finally. We'll go over and use Wolfram alpha and do all that stuff. But the diagram shows cross perpendicular uniform electric field E and magnetic fields B. The magnetic field B is to the right and the E field is directed into the plane. Okay, and they give us some strengths. The positive charge is not deflected from its straight line path perpendicular to both of the fields, and its speed must be blank. So this thing is moving down, and essentially it's not being changed, it's not accelerating, velocity is not changing, so acceleration is equal to 0 using Newton's second law is implying that the forces are going to be equal. So this is a Newton's second law problem. So you write down forces when you add them all together equals mass times acceleration, which is 0. So what are the forces? Well, you're going to have a magnetic field subtracted by an electric field, and those things are going to be equal to 0. So how do you calculate the magnetic field on a single charge? Well, that's QVB sine theta, where that's going to be the angle, minus EQ equals 0. So essentially this is going to select for the velocity. So these Q's cancel out. Everything's got a Q. You go and solve for the V. You get E over B sine theta. And if you notice, the sine theta is going to be 90 degrees. So that's asking the direction, the angle between the magnetic field, which is pointing to the right, and the magnetic field. So it's asking for the angle between the velocity and the magnetic field. That's going to be 90 degrees. So 90 degrees for sine is going to be equal to 1. This thing is going to be equal to just E over B. So we just got to take the one number and divide it by the other number. So we do that. We don't need a calculator here. So we have 4 times 10 to the 5 divided by 10 to the negative 1. So when you divide by 10 to the negative 1, it actually makes the number bigger. You get 4 times 10 to the 6. Is that an option? Yes, that is that option. There we go. So that's moving pretty dang fast. Again, the speed of light is 10 to the 8th, so it's about 1/100th of the speed of light. So that's still reasonable. We can still use some of these classical mechanics until we have to start using special relativity. Okay, let's keep going. Let's keep going. A long, thick wire of radius r carries a current I1 as shown in the figure. We like to determine the magnetic field inside the wire at distance r from the center of the wire where r is less than r. We can solve this problem using Ampere's law. You certainly can. So Ampere's law, I don't think we actually talked too much about it on any of the videos I've done. but it looks like BDL. This is going. I want to write down the calculus version first to remind myself what it looks like. But so essentially, I'm gonna, I'm gonna remind myself. Essentially, you pick a point, you do a path integral around. That's what this thing looks like over on the left. What you're adding up essentially the magnetic field times the small little displacements you do. So if we're going to write this in non-calculus version, it's going to be something like, b times these little changes in distance equals mu naught enclosed. And so if there's any current in here, so I think I used the wrong color, so I'm going to write the current, I'm going to write the path integral as a green. If there's any current in here that's passing through, we know that currents, when they go in a certain direction, they create magnetic fields that wrap around. So if I found a magnetic field wrapping around that still existed, persisted all the way through that loop, there had to have been a current that got pierced. So the left-hand side, how do we do this? So it turns out for a wire like this, again, it's like Gauss's law. This is very, very close to how we should think about and work with Gauss's law. That we're going to only use this when we have symmetry and when we can make a lot of assumptions. So this is also, there's this little cosine, I believe it's, yeah, that's still cosine. Essentially, this turns into just b times the length around. In this case, is going to be the circumference. When the B field and the direction that you're traveling around are always in the same direction. So if you're going in a circle, I'm traveling in a circle here, I'll notice that the magnetic field is always going to be in the same direction that I'm going to be traveling. So that's going to get rid of all these extra angles. It's really just going to be b times the circumference. What is b times the circumference? B times 2 pi, and it's going to be a little r. So this overall thing has a radius of big R, but I'm only traveling in this little circle that we can barely see with this picture, but it's going to be little r. That's what I'm choosing. So it's not going to be this one. It's going to be this one. What does the right hand look like? Well, it's not going to be the total I1. So again, we're only over here, we're only counting the current that gets enclosed. So we're not, you notice how we're not enclosing all the current, we're only enclosing this amount. So we actually need to use only a certain expression. So it's not going to be this. It's not going to be this one. So we could just go and say, oh, it's the next one down. But how do we know it's little r squared over r squared? Well, we could write this as the it's essentially it's going to be the it's going to have to do proportionally with the area. So it's going to be this total current, but the proportion of the area of r, enclosed by R1 and the one by big R. And we know that these look like, well, actually, let's write it down. We know that these look like pi r squared. So we get mu naught I1 pi R1 squared, pi r squared. So pi's go away. You get this stuff down here. So we get 1b and 2b. 1b, yeah, 1b and 2b. So it's got to be this one. That's our answer. Okay, let's keep going. It's been a while. We're still going. We're still feeling strong. We have like something like 4 or 5 left. We got this. A bar magnet is dropped north pole down so it falls through a circular piece of wire as shown in the picture. What direction is the induced current in the loop before it passes through the wire? Okay, what does the magnetic field from this look like? Well, it looks like pointing out from the north and going in to the south. So what's happening? So you're dropping it. So it's infinitely far away. And there's no magnetic field. There's no magnetic flux going through it. So you're going to use Faraday's law. You get closer, and eventually there's some amount of magnetic flux passing through it. So it goes from 0 to some amount, and it's pointing, roughly down when you add up all of them together. So it doesn't like that. Remember the view of loops, Faraday's law is telling us that this loop wants to create a magnetic flux that opposes this. And once it makes a magnetic field that opposes this change, it does not want or like change. It wants things to stay the same. So if I want to make a magnetic field pointing up, what direction does the current in the loop have to be? Again, we have to use the other right-hand rule and point our thumb in the direction of a current. So again, with this, just pick a certain place, pick a certain direction. We just know that when it wraps around, it has to look like, that's not the best picture. It has to be going in, when it goes through the middle, it has to be going up. But when it's on the outside, it has to be going down. So again, we're talking about the magnetic flux in the loop. So at this closest point, it doesn't have to be going left or right. So let's pick something. So I'm going to pick right. Turns out I picked right correctly this time. I wrap my hand around. So it's going like this. It's going, when it's in the loop, it's going to be pointing up. When it's out of the loop, it's going to be pointing down. So again, you just have to pick some point. If I pick left, it would be the wrong answer. The magnetic field would be looking like this. It'd be going up while out of the loop, down while it's inside the loop. So it's going to be looking like the picture I drew. So there's no induced current. That's not right. Before clockwise. So as viewed from the top. So we said that the current had to be going around like this. Had to be going around. So it's going to be before counterclockwise. Has to be. So we don't know after counterclockwise. After it passes through, then what's happening? So the magnetic field is still going to be pointing down, but now it's decreasing. The magnetic field, the magnetic flux is at a maximum when it's right through it. When it passes through, it's going to start decreasing. So it wants to oppose. It actually liked there being magnetic field. I mean, again, it didn't like change, but once it had that change, it doesn't want that to change. So it wants to make a magnetic flux going the other way, and we can pretty quickly see that it's got to be clockwise. Everything got reversed. And once to make a magnetic flux going the opposite direction, our answers get flipped. Okay. Hopefully that makes sense. Okay, let's keep going. Which of the following statements contradicts one of Maxwell's equations? So what are Maxwell's equations? So there's a lot of ways to write them down. I'm going to write it down the algebra safe way. We had Gauss's law, look like Q enclosed over epsilon naught. We have Ampere's law, which looks like delta L cosine equals Q mu naught I enclosed. We have Faraday's law, which just looks like epsilon naught equals negative n change at the magnetic flux over time. And then there's one that looks essentially like Gauss's law, but looks essentially, you just do the same thing for magnetic fields, and you'll find that that actually always equals zero. And always equals zero, kind of an oddity of nature, because what should go in there is magnetic charges. So as far as we understand, there actually aren't any magnetic charges. There's only electric charges. And so we lose a little bit of parity and symmetry we would have because we can't find these sort of things. So, you could have these charges create magnetic fields and they all go out, whatever. But you could also create electric fields by moving these around, and we would have to go backwards and add a ton of terms. But there's nothing precluding that necessarily. So let's look at this. The net magnetic flux through a closed surface depends on the current inside. I think this is true. Actually, is there more to this? Did I forget something? Let's go back to it. Isolated magnetic poles do not exist. So that's not, that's sort of a measurement. So we don't know that. So I don't think that's true, but let's keep going. The net electric flux through a closed surface depends on the charge inside. So that's exactly Gauss's law. So that's definitely true. A changing magnetic flux creates an EMF and a current. So that's just Faraday's law. So that is true. The net magnetic flux through a closed surface depends on the current inside. So that one, I think, is the one that's not true. So it would only depend on if there are net magnetic monopoles. So again, we talked about like dipoles, and dipoles really have a positive and negative on this side. And we had a question like this. This is a dipole. I have a positive end, I have a negative end. Monopoles are just, I have positives or I just have negatives, but I don't need more than one. So we don't know whether this is true, but that doesn't that seems wrong. The net magnetic flux through a closed surface. So it's these two ones that have extra terms that we we don't actually always talk about, but they're there. Again, what we talk about is some of the more simplistic and ways physics that we can present easily. The reality is always a little bit more complicated, especially when we're messy, especially with the math and using calculus, but there we go. Okay, we have an inductor with inductance L and a resistor with resistance R connected in series to a DC voltage source. Switch in this circuit is closed at time t equals 0. The energy stored in the inductor is at a maximum. So at all these different times. So recall that an inductor hates change. So the question is, the energy stored at the inductor is a maximum. Well, we can also write the energy. An inductor is 1/2 Li squared. So it's when the current's a maximum, things are changing the most. So when is the current a maximum? Let's think here. So when you close the switch, now this is a complete circuit, current starts moving and going around. It starts going around. But you just had essentially no current and then a ton of current. So this thing is effectively going to have a huge resistance. This inductor is going to have a huge impedance. It's not going to really change all that much. But after a very long time, that inductor is essentially going to settle down, contribute no extra resistance, and essentially just acts like it's not there. And that's actually going to be the moment when the current is going to be a maximum. The current is going to be maximum when the resistance of this is essentially 0, and this is the only resistance that matters. So it's going to be not any of these specific times. That's weird because there's no capacitors in this circuit to make things weird, to cause any oscillation. It's really just going to be a long time after the switch is closed. 1/2 Li squared will be maximized then. Okay, last question. Okay, we got there. Okay, a reflective solar sail receives twice the momentum imparted by light as a black absorber that reflects no light. If a very large 1 kilometer times 1 kilometer solar sail in the vicinity of Earth's orbit around the sun has an energy intensity of 1400 watts per meter squared incident upon it, what force will experience due to light? Okay, I talked about this a little bit in the last video, but the force exerted on a solar sail is essentially going to be the general intensity of light times any type of cross-sectional area. Again, that's going to be the watts per meter squared, so we need to multiply by meter squared to get watts, and then divided by the speed of light. And then we also have a factor of 2 that gets involved because the light is hitting it, it's reflecting off, it's imparting double the momentum as otherwise. So the intensity is 1400. The area is going to be 1 kilometer times 1 kilometer, so it's going to be 1 to the 3 squared divided by 3 times 10 to the 8 times 2. So let's collect all of these terms together. We have 1400, so essentially we have, and then we have 2, so we have 28 divided by 3. We have times 10 to the 2 times 10 to the 6 divided by 10 to the 8. So those are all going to go away. And so essentially we get 28 divided by 3, and that's 9.3 repeating. So what answer is that? So that's going to be this one. So I mean, that's a huge sail, 1 kilometer times 1 kilometer, giant square. Even then, that's 9.3 watts, and that's like that much force that I exerted there. That's that's really nothing. So that's maybe not the most practical thing to build a solar cell in this way. So that's it. That's going to be all that we're going to be doing for review. I really hope whatever you're doing works out. Hopefully this gives you a good idea and some refresher about all the things we've been talking about. But good luck whatever you're doing. Thanks for joining me as always. Okay, bye.